Hiya. So in this video, we're going to continue looking at the vector product. Sorry about the length of the last video. In essence, we gave a definition for the vector product in the last video. It took a nice 15 minutes almost to define what a vector product is. We had a million conditions. We said, oh, we need this orthogonality condition. We need this anti-commutativity condition. We need this linearity condition. We need this length condition, and then we want this orientation condition. So we have 1, 2, 3, 4, 5 different conditions. 5 conditions for a vector product. Does it actually even exist? And does it actually define what we want? So in this video, we're going to be talking about precisely that does it exist and is it unique? In other words, if I take two things and I multiply them together, could I is there maybe some other way to get this vector product without making this big, long, complicated list of axioms? So we're going to try to do this. So we're going to show this for 3 dimensions. And first we're going to show that it exists. So we're going to start off with is some orthonormal basis. So we start off with some orthonormal basis. And we want it to have the same orientation as V. So same orientation as V. Now, what we want to do is we're going to assume that a vector product exists. Are we doing... Yeah. Yeah, we're first starting off with uniqueness. So start with uniqueness. Where is that? Here we go. So first, we shall begin by showing that if it exists, then it's unique. So unique. I'll put uniqueness here. So we know that's what we're showing. And I will actually do this in pink. Okay. So since we're trying to show uniqueness, we're going to assume that a vector product exists. Okay, so since we know a vector product exists, we know that, first off, that EI times EI, right? EI cross EI, what is this? This is always going to be equal to 0, right? The cross product of any two vectors of the same vector is always 0. If I look at E1 cross E2, now the perpendicular axiom, so the very first axiom, is basically telling us that this is equal to lambda E3, some scalar multiple of lambda 3, right? This is because we have the basis that we have this condition here, that these 3 are equal to 0, and that this gives us a basis. So in other words, lambda E3 has to be this third condition. By the length condition, this has to be just plus or minus of E3. So the length condition here, if we recall, is precisely this. So since they're perpendicular, then it has to just be x times x. So here this is just, this is equal to E1 times E2, which is equal to 1 times 1, right? So the length has to be 1. So in other words, lambda is equal to 1, plus or minus 1. And then by it being the same orientation, we're forced to actually have positive 1. So same orientation. Now, since these 3 bases, 1, 2, 3, these are all the same orientations. I won't go into this too much, but basically this is, you just flip adjacent things and that gives you enough switches, keeps the orientation. They all have the same orientation, which basically tells me that E2 cross E3 gives me E1, and E3 cross E1 gives me E2. Sorry, minus E2. Wait, no, E2, this was right. E2. And then by anti-commutativity, we have the opposites here. This is minus E3, minus E1, minus E2. All right. So we have these three. And then from here, we have everything on an orthonormal basis. So this, for any product, for any pair of elements, in an orthonormal basis, we have this condition. So we have the cross product on any pair of elements in an orthonormal basis. But we don't want this on any, on just the basis. We want it on any element. And we can actually do this by linearity. So we can kind of do this explicitly if we wanted. It's already in the notes. I'm not going to rewrite this whole thing. But in essence, what we have is we start off with two vectors, v and w. And I look at the cross product of v and w. So here we have v, here we have w. And then I actually do the linearity, right? So I use linearity or bilinearity. And I'm left with this whole thing. Some of these are in red. And that's because these ones, these three, the ones in red, these are all just 0, right? So this gives me 0. This is, oops, not this one. This gives me 0, and this gives me 0. And then if I look at, for example, E1 cross E2 here, and E2 cross E1, I can put them together. I can replace these, right? So this E1 cross E2, this is E3, and this one is minus E3. And we can kind of see this when I look at here, right? So this is V1 W2 minus V2 W1. So this gives us this big formula, which is in terms of this. And this we can actually represent in matrix form if we wanted. So this is basically showing us uniqueness, right? Like this is uniqueness in the sense that once we have these 5 conditions, notice how we used all of them, right? So the 5 conditions we used is 1, 2, 3, 4. I'm missing one. Where's the 5th one? Oh, the 5th one is linearity, which is here, right? So 5. So we used all 5 conditions to kind of show that these things happen. So we have uniqueness. And then what we can actually do is we can represent this. So if we look at this vector here, we can actually represent this in a matrix form. This is just the determinant of the following: E1, E2, E3, V1, V2, V3, W1, W2, W3. So if you take the determinant, this formula up here and this formula down here are going to be, the same. So we're going to kind of stop here for now. The rest, so the existence is actually left for an exercise. So we're going to leave it for that. And what we're going to want to show is that, in essence, that this satisfies all of the required axioms. In other words, if I take this determinant, that this gives me all of the things. Yeah. So, in other words, we're going to go backwards. In other words, if I look at this formula, right, on the bottom, and I say this is precisely the vector product, we want to show that this satisfies all 5 axioms. So we want to show formula satisfies all the required axioms 1 to 5. And this is left as an exercise. So we'll stop here. Sorry that some of the videos in this week were a little longer. Luckily, we have just less videos and less minutes all together. So hopefully it wasn't so bad. I will see you all in lectures, and I will see you all next week for week 5. So we'll stop here.